Okay, so let's proceed. So the last time we were here, we were talking about the difference between a strong acid and a weak acid. And before that, we talked about strong electrolytes and weak electrolytes. And basically the concept behind all of that discussion is the same. Just to recap a bit, strong acids will undergo complete dissociation, and therefore they are very strong conductors of electricity, while weak acids will undergo incomplete or partial dissociation, and therefore, as a result, they will not conduct electricity as well. And the example of a weak acid that we have here is acetic acid. I think the example of a strong acid that we looked at before, let me just go back a bit. Okay, we didn't have that, but an example of a strong acid would be hydrochloric acid. In fact, the next slide is about how do we determine a strong acid versus a weak acid. And in terms of how we conventionally write down the formulas for these acids, usually the strong acids are written such that the hydrogens are in front. So for example, in the case of hydrochloric acid, it's HCl. In the case of sulfuric acid, it's H2SO4. So the hydrogens are always written first in the case of strong acids, in the formulas of strong acids. And then when it comes to the formulas of weak acids, such as acetic acid, the hydrogen that is ionizable, in other words, the hydrogen that would leave the structure to form the ions, would be placed at the end of the formula. So that's one way of distinguishing between acids in terms of how they're written. But apart from that, this is basically what you're going to use to determine the difference between strong acids and weak acids. So these acids you need to memorize as strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. Pretty much all other acids you will encounter would be weak acids unless you're told otherwise, all right? So you need to memorize these 6 acids as strong acids. Now, let me say a little bit of something about the sulfuric acid, because you'll notice that the difference between the sulfuric acid and all the other acids is that it has 2 hydrogen ions that can be released when the sulfuric acid dissociates. And it turns out, and I'm just going to pull up my writing pad here, it turns out that in the case of, let me get rid of this here. Okay, in the case of sulfuric acid, the ionization can take place in 2 steps, all right? So the first step would be what you see here, where you have H plus HSO4 minus, all right? And this is a strong dissociation, all right? In other words, basically all of the H2SO4 molecules will be converted to ions, H plus and HSO4 minus. Now, this here, which was produced in the first step, can itself release another hydrogen ion to form these products. All right? But it turns out that unlike the first step, the second step is not a strong dissociation. So I need to replace that arrow with the reversible arrows like this, right? So this dissociation is weak, all right? So that's basically what happens in the case of sulfuric acid. The first dissociation is very strong, right? Produces these ions in high abundance, relatively speaking. But when this undergoes the dissociation in the second step, the concentrations resulting from that dissociation is very small, right? So you'd expect that the concentration of the sulfate ion in this solution will be very small compared to the concentration of the hydrogen sulfate ion. So I thought I should just make mention of that fact, all right? It's kind of, sulfuric acid is kind of unique in this regard as a strong acid. Okay, so let me go back to that one here, all right? Okay, so if you understand, of course, the concept of strong acids and strong acids and weak acids, then you should be able to appreciate and understand the concept behind strong bases and weak bases. So the definition of a strong base is given here. These are typically ionic hydroxides that undergo complete ionization in water, and therefore, again, as in the case of strong acids, they are good conductors of electricity, right? So a good example of a strong base would be sodium hydroxide. because sodium hydroxide will undergo complete dissociation in water to form Na plus OH minus, right? So that's a strong base. All right. So weak bases, on the other hand, they undergo partial dissociation. Now, typically these are not ionic, or I should say, well, ionic hydroxides, but when they're added to water, they produce hydroxide ions. So that's the reason why they're called bases. Now, a very common example of a weak base would be ammonia, right? If you take ammonia and add it to water, I think I have the equation. No, I don't have it here. So let me go to my writing pad again. In the case of ammonia, NH3, when added to water, what you have is the formation of ammonium ion and hydroxide ions, right? And it is the production of the hydroxide ion that makes ammonia a base. And because this is a reversible process where you have the back and forth between the reactants and the products, that makes the ammonia a weak base, all right? So therefore, in the case of ammonia, the concentration of OH minus would be very low. So the concentration would be low for the hydroxide ion and also for this, right? These two would have low concentrations, and therefore this solution would be a poor conductor of electricity, all right? So that's the difference between a weak base and a strong base. There are other weak bases. They're mainly organic, all right? In other words, they have carbon in them. So just to mention, let me go back to my writing pad here. Just to mention a couple of examples of organic bases. You have this compound known as methylamine. You have this compound known as dimethylamine. And this compound known as trimethylamine. These are just 3 examples I'm writing here. These are all organic bases, and they basically behave the same way as ammonia in that when they are added to water, produces a solution which has a relatively low concentration of hydroxide ions. Okay, so that's as far as that is concerned. All right, so we talked about strong acids, strong bases. I'm sorry, strong acids and weak acids, and then strong bases and weak bases, all right? In terms of recognizing strong or weak bases, it's actually easier to memorize this table right here. These are the hydroxides of group 1A and group 2A metals. These are all strong bases, all right? Pretty much any other bases that you're going to meet in this course will be considered to be weak bases, again, unless you're told otherwise, all right? Okay, so you need to memorize these, which are easy to remember because they're just from group 1A and 2A. Okay, so let's talk about the reaction between acids and bases. So this reaction is called a neutralization reaction. And basically, this happens when you react both of them together, what you end up with, at least in theory, is a product which does not have either acidic or basic properties. In other words, it's neutral. Now, I said theoretically because in actual fact, that is not always true, but I won't get into that right now because that's a topic for discussion when you get to general chemistry 2. In general chemistry 2, you're going to realize that not all acid-base reactions result in a neutral product, all right? In some cases, you're going to get a product which is acidic. In other cases, you're going to get a product which is basic, but we won't get into that right now, all right? So here's an example, a very simple example of an acid-base reaction, the reaction between hydrochloric acid and potassium hydroxide to get water and potassium chloride, all right? And very often when we do this reaction in experiments, especially when it comes to titration, which we're going to talk about later, we add a substance to the mixture called indicators. And the indicators, as the term suggests, indicates that point when you add just the right amount of HCl to potassium hydroxide or vice versa stoichiometrically, all right? We're going to get into that discussion later on in this chapter. But for now, we're just going to talk about neutralization reactions and how do we determine the products of the neutralization reaction. Okay, so basically, and I think we discussed this already, but let me just give a quick review. Let me go back to the writing pad here. Let me clean this up. So just to remind you, no. Okay, so just to remind you, to figure out what the formula for the products are, sodium hydroxide is one of the reactants, which is the base, and hydrochloric acid is the other reactant, which is the acid. So basically, remember, we combined the hydrogen from the acid with the base from the hydroxide from the base, and that gives you one of the product, which is water. And therefore, the other product will come together as a result of the sodium coming together with the chloride to form sodium chloride, all right? So that's basically how you get the products. And of course, you should ensure that the equation is balanced, which in this case it is. We don't need to add any coefficients to balance this equation, but there are other cases where you may need to do that, all right? So that's just a brief review of determining the products of an acid-base reaction. Now, what you're going to find is that what we're going to learn about today is how we write what we call the net ionic equation, right? What I just described to you is oftentimes referred to, this equation here of this type, is oftentimes referred to as a molecular equation, which is a bit of a misnomer because not all the substances involved in this reaction are molecules. Sodium hydroxide is definitely not a molecule. Sodium chloride is not a molecule. The only molecules that are present in this case would be water and the HCl. And even in the case of HCl, as we're going to see later, it does not exist in water as a molecule because it's a strong acid, all right? So this term is not accurate 100%, but it's a term that is used in most textbooks to describe this type of reaction, all right? Now, what we're going to learn about is how do we get from this equation to what we call the net ionic equation. Now, first thing we need to do is write down the molecular equation, which is what we have here, all right? So the next thing we need to ask ourselves is, will these substances, each of them, will they exist as intact substances or will they dissociate in water? Because this is an aqueous environment that we're dealing with. So first thing we look at is the hydrochloric acid here. And if you recall, we said that hydrochloric acid is one of the 6 strong acids. So therefore, because it's a strong acid, it will undergo complete dissociation. Potassium hydroxide is a strong base, so that will undergo complete dissociation as well. Water is a molecule. Molecules do not undergo dissociation usually. Very unusual for it to undergo dissociation. And it certainly won't undergo dissociation, excuse me, in this case. And then we get to potassium chloride, which is in an aqueous solution. Any ionic compound which is in an aqueous solution will undergo complete dissociation, right? So we can go from this, which is a molecular equation, to this, which is now the ionic equation, which shows you all the ions that will result from the dissociations I described. So the HCl here will undergo dissociation to form H plus aqueous and chloride Cl minus aqueous. The potassium hydroxide here will undergo dissociation to form K plus aqueous and hydroxide aqueous. The H2O here will not undergo dissociation, so it will remain intact. And finally here, the potassium chloride, because it's in an aqueous solution, will itself undergo dissociation to form K plus aqueous and Cl minus aqueous, all right? So this equation here, the second equation, is called the ionic equation. So let me make a note of that. So the first equation is called the molecular equation. The second equation, just write it here, is called the ionic equation, all right? Now, the next step to get to the net ionic equation is that we have to identify those species that are identical on both sides of the equation, of the ionic equation. And we call those ions spectator ions, all right? Spectator basically means that, you know, they undergo no real change. They basically remain in the same state before and after the reaction ends. So if you examine this equation closely, you'll see that there are 2 ions that would be referred to as spectator ions. One of them would be the chloride ion here and here, so we cancel them out. And the other one would be the potassium ion here and here, all right? So these are the spectator ions. So once we cancel them out, we simply write down what is remaining. And what do we have remaining? Basically, we have H plus reacting with OH minus to form H2O liquid, all right? So this is what we call the net ionic equation for this reaction. So this is basically the reaction that is actually taking place in this particular situation. The potassium and the chloride ions basically do not participate. All they do is sit around and watch what's happening. The more active ions involved would be the H plus and the OH minus. And of course, the water would be produced on the other side, all right? So that's how we get our net ionic equation from our molecular equation in the case of an acid-base reaction. Okay, are there any questions about this? Any questions? Any questions? Okay, so what I'm going to do is do another example, which is a bit more complicated. Let me go back to my writing right here. And let me clean this up. Okay, so let's look at another acid-base reaction. This time it is H2SO4 plus, okay, what's going to be the base? I'm going to use sodium hydroxide as a base. All right. And these are all aqueous. And by the way, when you're doing this exercise, make sure that you include the state symbols, right? That's very important. To form, let me see here, to form Na2S, whoops, sorry. Na2SO4 aqueous plus H2O, liquid, all right? Okay, so this would be the molecular equation. So the first thing you need to do is balance this equation. So how would we balance this molecular equation? Anybody?
You need a 2 in front of sodium on the left side.
Okay, so a 2 here.
Yeah.
Okay, what else, if anything else?
I think that's it.
I believe
You
it's
sure?
balanced now.
You sure? I don't think so. Count up the oxygens on both sides. How many oxygens do we have on the left side? We have 2 here, and we have 4 here, so that's 6. How many do we have on the right side? We have 4 here plus 1, 5. So the oxygens are not balanced.
We should add a 2 at the H2O at the right side.
Exactly, 2 here. And now the equation is balanced. Everything is balanced if you check it out. You have 4 hydrogens on both sides. You have 1 sulfur on both sides. You have 6 oxygens on both sides. You have 2 sodiums on both sides. So everything is balanced, all right? Okay, so now that we have the molecular equation balanced, now we need to write down the ionic equation. So we have to figure out now which substances will exist as ions, will dissociate to form ions, and which substances will remain intact. So let's start with the sulfuric acid, all right? So will that dissociate, and what will be the products of the dissociation for the sulfuric acid? Now remember we said that sulfuric acid is a strong acid, right? So what will be the products when sulfuric acid dissociates? Anybody? Remember what I said about sulfuric acid? Let me see here. Remember what I said about sulfuric acid when I showed you this slide? What did I say about sulfuric acid? Well, come on, guys. I just said it like 5 minutes ago. What did I say about sulfuric acid? Remember I said that sulfuric acid, the first dissociation is strong. H2SO4 will undergo first dissociation, which is H plus HSO4 minus. And then the second dissociation is weak. Draw a line here to separate it. HSO4 minus to form H plus and SO4 2 minus, right? So therefore, when you add water or when you add sulfuric acid to water, this is what you're going to get mostly. You will not get sulfate ions by itself. So to start off with this, to dissociate it, you're going to get H plus aqueous plus HSO4 minus aqueous. All right? Okay, so what about the sodium hydroxide? What will be produced? Well, sodium hydroxide is a strong base, so therefore we know it will undergo complete dissociation. So what would be the product when sodium hydroxide undergoes dissociation? Anybody? Come on, you should be able to figure this out based on what we discussed. Let me show you the slide. Remember what I said here? Potassium hydroxide will dissociate to form K plus and OH minus, right? So in the case of sodium hydroxide, what will be formed when it dissociates? Anybody? Well, come on, guys, come on. Can you guys hear me?
Yes, I'm working on it.
Oh, okay. I was wondering if I'm speaking to myself. This should be easy. If you understood what we discussed a while ago, then you should be able to predict what would be the products of the dissociation here. One minute, let me turn on the fan in here. Hold on.
I'm not sure.
Okay, so in the case of sodium hydroxide, when it dissociates, it forms Na plus aqueous, which is the sodium ion, and the hydroxide ion, right, aqueous. However, you have to keep in mind that you have a 2 here. That 2 affects all of the ions here. So therefore, you have to place a coefficient of 2 here, and a coefficient of 2 here. So that's basically what happens in the case of the dissociation of sodium hydroxide. So we have taken care of all the reactants so far. So now we have to look at the products. So what about this? This is aqueous. It's in an ionic, compound in an aqueous solution. So what that means also is that it will dissociate as well. So what do you think would be the products of the dissociation of sodium sulfate? No, you should be able to do this based on what we did here and what we did here. So what would you expect the products of the dissociation here?
Would it be 2Na
2Na
plus
plus aqueous plus,
4SO
you mean SO4?
or SO4? You're gonna leave
Right.
it like that.
Yeah, SO4 2 minus aqueous. Exactly. So those will be the products when the sodium sulfate dissociates in water. And then finally, we have H2O, which is a covalent compound in a liquid state that will not undergo dissociation. So we simply rewrite this down here, plus 2H2O liquid, all right? Okay, so the next step is to determine the net ionic equation, all right? So if you remember, we said that to get to the net ionic equation, we have to cancel out those items that are common to both sides, right? So I want you to look at the ionic equation that we have here and tell me what ions are common to both sides.
Two Na is common.
2Na plus here, 2Na plus here. And is there anything else? Oh, by the way, I realized I made a mistake. You know this 2 right here for the 2 hydrogens here? That means that 2 should be here. All right, so please make a note of that. All right, I somehow missed that for some reason.
Since there's supposed to be a 2 there.
Oh, no. My bad. Forget what I just said. I'm thinking of something else. That's correct, actually. That's correct. I thought the 2, I had a mental lapse. I thought for a minute that the 2 hydrogens were produced upon dissociation, but it's only 1. I'm sorry. Okay, so just forget what I just said. Okay, so where was I? Okay, so you correctly said that these 2 are canceled out and there's nothing else that will be canceled out. So therefore, you just write down what is left, which would be H plus aqueous plus H SO4 minus aqueous plus 2OH minus aqueous. Okay, so that takes care of the left side. And then on the right side, we have SO4 2 minus aqueous plus 2H2O liquid. And that would be the final answer. All right. Yeah, so that's it. All right. And you can do a last check through to make sure that everything is balanced. So for example, the hydrogens, you have 1, 2, 3, 4 on the left, and you have 4 on the right. You have 4 plus 2, 6 oxygens on the left, 4 plus 2, 6 oxygens on the right. And then you have 1 sulfur on each side. And then you have no charges, or I should say, let me see here, hold on. This plus charge here will cancel out the negative charge. So the total charge on this side is -2, and the total charge on this side is -2. You have to make sure that the charges are balanced as well. In other words, the total number of charges on the left should be equal to the total number of charges on the right. All right? Okay, So that's basically how we would do, again, another example of determining the net ionic equation of an acid-base or neutralization reaction. Okay, any questions about this? Any questions?
Can you remind me what that last state is? But not aqueous, but that last one next to 2H2O.
Liquid.
That's liquid, and
Yeah,
it's different from aqueous.
Exactly. And that's a very important point. It's different from aqueous. Aqueous means basically a particular substance is dissolved in water, right? Liquid could be water, but it could be other things. You can have liquid ammonia, you can have liquid whatever, right? Different substances, acetone, whatever. So yes, please make a note of that. Those are two different states, all right? Okay, any other questions about this? Any other questions? All right, so let's go back to.
Are there the same amount of positive charges on both sides?
Well, the net charge would have to be the same. You don't have to have the same number of a charge of a particular type. So in other words, when you add up all the charges on the left, it should be equal to the sum of all the charges on the right. So if you look at this one here, you'll notice that you have, let me do it this way. Let me erase this here. Let me do it this way. This is probably a better way of explaining it. When you count up all the charges here, you have 3 negative charges plus 1. So basically plus 1 minus 3 gives you minus 2, right? So you have a total of minus 2 on the left side. And here you have only a minus 2 charge on the right side. So therefore the charges are the same on both sides. All right? So you don't have to have the same number of plus and minus charges individually. What you must have is the total number of charges on the left side being equal to the sum of the charges on the right side. All right?
All right, thank you.
Okay, no problem. Okay, so let me go back to the PowerPoint here. And let me bring this over here. And let me do this. Okay, let me just make a mention about titration. Unfortunately, at least for my lab courses, we won't be able to do this in person, which is a real shame because I think this is an experience that, you know, students can benefit from, just actually seeing how this process works. Right now, titrations is basically a process where you have one reactant for which you don't know what its concentration is, and then you add carefully another reactant whose concentration is known, and you add the other reactant until you add the right amount to consume the first reactant. All right, and then you do some calculations to find out the concentration of the unknown reactant, the unknown concentration of reactant, right? So the way we do this is that we place one reactant in a piece of glassware known as a burette. Let me see if I have a diagram of it here. No, I don't. Okay, so I'm going to, this is my, let me apologize for my lack of artistic skills. I am not in any way talented as an artist, unlike my brother. Okay, what's going on here? Oh. So this is my interpretation, please don't laugh, of what a burette looks like. It's a long cylindrical piece of glassware, kind of look like this. And then there's a tip at the end of it, fitted with a stopcock or a tap. All right. And they come in different sizes. Now, the one that we have in our labs, it's a 50 ml burette, meaning that it's graduated where you have 0 at the top. So this would be 0.00 mils. And then you have a mark down here which says 50.00 mils. All right. So basically, you would add one liquid here. Now, in this example, I'm going to use a base, right? So let's say the base is 0.10 molar sodium hydroxide, all right? So that's your base. So what you do is, of course, in practice, actually, let me just erase this here. this part here. In practice, what you should do for the sake of avoiding spillage is that you put a funnel at the top here. So you have your funnel here, which allows you to more easily pour your base solution into it without spilling it, all right? And then, so typically what you do is add your base until you get to the 0.00 mark or close to it. You don't have to get exactly 0.00, as long as you can record the volume, the initial volume reading. And then you have your acid down here in a flask, usually, right? So this would be your acid solution, right? Let's say that you don't know what the molarity is. So the aim of this exercise is to determine the molarity of your acid solution, all right? So in addition to the acid, you're gonna add the aforementioned indicator. The indicator basically changes color upon addition, well, depending on its environment. So it will have one color in an acid environment and another color in a basic environment. Now, for the experiment that we normally do in the lab, the indicator that is used is an indicator known as phenolphthalein. And this indicator is pink in base and colorless in acid, all right? So basically, if you're using this indicator here in this acid solution, it's going to be colorless, all right, initially, before you add any base to it, all right? You need to also record the volume of the acid solution that you're going to use, all right? And then what you'll do is you'll open up this stopcock and then you allow the acid, you allow the base to be added to the acid, right? So you add the base dropwise, and then what you'll get happening is that you're going to see a pink color up here, but that pink color will disappear when you swirl the flask. So in our labs, what we typically do, we have the students work in pairs. One student will control the flow of the liquid by adjusting or turning the stopcock. The other student will be swirling the flask underneath it, making sure that the solution of base goes directly into the acid solution. And as the student that is swirling, as he or she is swirling that solution, the solution will become pink in color, but this pink color disappears. And that continues until one drop of the base will make the solution completely pink. That means that the person who is controlling this will immediately turn it off, and then you will record a new reading. So the base level in the burette will fall to a lower level here. So let's say that this becomes, let's say the reading that you get here is, I'm just going to make up a number here. Let's say it's 23.21 mils, right? And let's say, so this is the final volume reading and the final burette reading. This is the initial burette reading, right? So therefore, the amount of base that would have been added here would be the difference between these two readings here and here. So therefore, the volume of base added would be equal to 23.21 mils minus 0.00 mils, which would be equal to 23.21 mils, all right? So that's basically, that's just a quick description of how this particular experiment is done. As I said before, unfortunately, at least for my lab class, we won't be able to do this because it's really a nice experiment and it shows you, it utilizes basically a lot of things that you would have learned in lecture. It utilizes the mole concept, concentration calculations, and it's a good analytical experiment so that you have an appreciation for, what we do in the lab in terms of analyzing solutions, determining their concentrations, and so on, all right? So that's basically how titration works. The type of titration that I described here, we call this an acid-base titration. Let me write this right here. Acid-base titration. All right, this is just one type of titration process. There are other types of titrations. There's redox titration, precipitation titration, and others, you know. So this is the simplest example of a titration, however, all right? Okay, any questions about this? Any questions about the titration process? Okay, so let me continue our discussion. Okay. Okay, so let's talk about some acid-base reactions which involves the formation of gas. Now, there are certain anions which, when you add acid to them, will produce gases, right? And these are the ions that are listed here. And I'm just going to go through each of them so that you have an understanding of what's happening here. So for example, well, let me just say this. So for example, in the case of any compound that contains the carbonate, or I should say the bicarbonate ion, if you add any acid to it, which of course contain hydrogen ions, you're going to end up with the formation of carbon dioxide and water, all right? And this is something that you can actually do at home. In fact, that's what's being demonstrated here. So I'm quite sure you guys are familiar with baking soda. Baking soda is basically sodium bicarbonate, so therefore it contains the bicarbonate ions. And if you add lemon juice to it, which contains hydrogen ions, then you're going to see fizzing taking place, some bubbles being formed, and that would be due to carbon dioxide being formed, and the other product would be water, all right? You can also use vinegar as well to do this. Vinegar contains acetic acid, which contains the hydrogen ions, and this very same reaction will take place, all right? So that's what happens in that case. In the case of carbonate ions, any compound that contains carbonate ions, if you add acid to them, that would also produce carbon dioxide and water. I'm not sure if this can be done at, well, yes, this can be done at home actually. I don't remember seeing this being sold in stores anymore, but you have a substance called washing soda, which is sodium carbonate, all right? That substance, when you add acid to it, will produce carbon dioxide and water. Again, you can use lemon juice or acetic acid to carry this out, all right? So these two reactions you can actually do at home. Now, the next reaction here is one involving either hydrogen sulfide or the sulfide ion. If you add acid to any substance which contains these two ions, you're going to get these two products, sulfur dioxide and water. Now, the thing about this reaction is that I would not recommend that you do this at home because sulfur dioxide is a gas which, if you inhale it, you start coughing and choking and all of that. So I definitely would not recommend that you do this at home, all right? Then we have these two anions, the hydrogen sulfide and the sulfide ions, right? If you add acid to any of these ions, then you end up with this gas, which is known as hydrogen sulfide. Hydrogen sulfide is a gas which, again, I wouldn't recommend that you do this reaction at home because hydrogen sulfide is a gas which, for one, smells very horrible. It smells like rotten eggs, all right? In fact, the rotten egg smell that we're all familiar with is due to the formation of hydrogen sulfide as a result of some decomposition reactions of proteins in the egg, all right? So hydrogen sulfide gas is not a very pleasant gas to inhale. And not only that, it's a very toxic gas, right? If you inhale enough of it to the point where you don't smell it, then you're in serious trouble because what that means basically is that the hydrogen sulfide has been built up in your bloodstream to a very toxic level and you're basically close to death at that point. So for those two reasons, I would not recommend that you carry out this reaction at home, all right? You'd have to do this in a lab with special equipment and all of that, all right? Okay, so these are just some gas-forming reactions as a result of acids reacting with certain anions, all right? And you need to know these, all right? And what you see here, all these equations here are net ionic equations, right? You can actually write down, starting with the molecular equation and work your way towards each of these reactions or each of these net ionic equations. Okay, any questions about any of these? Any questions about these reactions? Okay, so continuing. Okay, so now we're going to get into a discussion of what we call precipitation reactions. Now, what do we mean by precipitation reactions, right? A precipitation reaction is one where you have two solutes in aqueous solutions, separate, let's say in separate test tubes, and then when you mix them together, you get the spontaneous formation of a solid, right? So if you have two clear solutions and you add them together and you get a solid being formed out of those two clear solutions, then you have what is called, that solid is called a precipitate, and that reaction is called a precipitation reaction. And I think the example that is shown here is the reaction between, if I'm not mistaken, lead 2 nitrate and either sodium or potassium iodide. So let me write down, I don't think I have the equation. Let me see here. No, I don't have the equation here. So let me write down the equation in my writing pad here. So I'm thinking that the reaction is potassium iodide, aqueous, plus lead 2 nitrate, aqueous. All right. And this is a double displacement reaction. If you remember from your General Chemistry 1 class, in a double displacement reaction, you have an exchange of ions between these ionic compounds. So one of the products would be PbI2, and the other product would be potassium nitrate, KNO3, all right? And turns out that this would be the solid that is formed. So this is the precipitate, and the potassium nitrate will basically remain in an aqueous solution, all right? So that's basically what is happening in this particular example. And this is a typical precipitation reaction. Okay, now one problem that students will face when figuring out the precipitation reaction is, how do you determine which product will be the precipitate? How do you determine which product will be the solid and which product will remain in aqueous solution? Or will you have a situation where both products would be in a solid state or both products would be in the aqueous state? All right, so in order to figure that out, there's a table that is provided in Canvas, which looks like this chart, all right? This is a chart that you would use to make predictions as to whether or not a precipitate will form in a reaction like the one that I just wrote a while ago, all right? So you don't need to memorize these, but you need to know how to use this chart to make predictions. So for example, just to point out the first line in this chart, it says, almost all nitrates, acetates, perchlorates, group 1A metal salts, and ammonium salts are soluble. So basically, any particular ionic compound that meets the criteria listed in this line right here, you can assume that they will dissolve in water and therefore will not form a solid, all right? Let's look at the second line. It says most chlorides, bromides, and iodides are soluble, with the exceptions of lead 2 plus, silver plus, and mercury 1, all right? So any particular ionic compound which meets this criteria will be soluble, excepting any chloride, bromide, and iodides of these ions. And that's the reason why I knew that, going back to this, that lead 2 iodide is a solid, because the chart says the exception would be lead 2 plus of any iodides, right? So lead 2 iodide would be a solid. It will not dissolve in water. And that's the reason why I know that this would be in a solid state, and that's why I put S here, right? The first rule will predict that the potassium nitrate is aqueous, because going back to the rule, it says that all nitrates are soluble, right? So therefore, any nitrate, it doesn't matter, will be soluble. So we know that potassium nitrate will be soluble. Furthermore, potassium belongs to group 1A. And it says here, all group 1A metal salts are soluble. So therefore, based on those two facts, we know that potassium nitrate will be soluble, all right? So that's important when it comes to writing down the net ionic equation, which we're going to get to later on, because we have to know which substances would be solid in a solid state when this reaction takes place and which would remain in an aqueous state, all right? So with that said, let's move on to the next step in this process. Let me erase this here. So what I'm going to write down here is that this would be the molecular equation. Again, remember I said that this is a bit of a misnomer, especially in this case because there are no molecules involved, but that's basically the terminology that's adopted in most textbooks. Okay, so the next step, if you remember when we look at the acid-base reaction and determining the net ionic equation of such reactions, you remember that the next step is the ionic equation, all right? And for the ionic equations, we have to determine which substances will dissociate to form O. I just realized I'm jumping a step. Before we get to the ionic equation, we need to balance the equation. That's very important, right? We need to balance the molecular equation. So how do we balance this molecular equation? Anybody? How do we balance this molecular equation?
There are 6 oxygens at the left, isn't there?
Yes, sir. Right here, yeah.
So at the very least, we can start with putting a 2 at the right where KNO3 is.
Okay, so we put a 2. This thing is not behaving itself. Okay, so we put a 2 there. Anything else?
Put a 2 at the KI at the beginning.
Okay.
Yes.
Anything else?
There's 2. What's N stand for at the right? And there's only one N at the left so far.
Well, we have 2 nitrogens here, and this 2 here affects the nitrogen here.
Oh,
So
whoops, that's right.
yeah, we have
My
2
bad.
nitrogens on both sides, right? Yeah, I think this equation is balanced actually. All right, let me erase this here. Erase this here. Erase this here. Okay, so let's see if you can get the ionic equation. Remember what we did the last time. Basically, we try to determine which of these substances will form ions. So let's start off with the potassium iodide. What would be the ions formed? Because it's an ionic compound in an aqueous solution. Any ionic compound in an aqueous solution will undergo dissociation. So what would be the ions that would be formed as a result of the dissociation of potassium iodide? Anybody?
Ask your question again.
What would be the products of the dissociation of potassium iodide? What would be the ions formed?
We 2K positive,
2K plus, aqueous,
aqueous, and then I negative aqueous.
2I minus aqueous. Remember, the 2 here multiplies the potassium and the iodide. So therefore, that's why we need a 2 here and a 2 here, all right? Okay, so that takes care of that. What about the lead 2 nitrate? When that dissociates, what will be formed? Again, it's ionic. Again, it's in an aqueous solution. So what would be the products formed when that dissociates? Anybody? Well,
Would you have to do like 2 PB because of the
nope. This 2 here only affects what's within the parentheses here.
okay, so it'd just be PB positive.
PB 2 plus. You have to figure out the charge as well, right? We know it's 2 plus because nitrate has only 1 minus charge and there are 2 of them. So therefore that means that the lead must carry a +2 charge.
And it's aqueous.
And it's aqueous as well, correct. Okay, and what would be the other ion?
NO6 plus?
Mm-mm. NO what? Anybody else? You're right about the NO, but you're wrong about the subscript here. NO what?
Well, I assume it's aqueous, but
Yes, you're right, it's aqueous, but you need to figure out, or you need to give the number here, that is coefficient, the subscript.
NO minus?
Well, there's a minus sign here, but there's a subscript down here. And it's the same as the subscript here. So that's going to be NO3 minus, right? But because of this 2 here, you need to put a coefficient of 2 in front. Everybody see that?
I understand.
And that's aqueous as well, all right? So that takes care of the left side of the equation. So we have our arrow, but we need now to take care of the right side. And on the right side, we have these 2 compounds. We have lead iodide, lead 2 iodide, and potassium nitrate. So the thing about the lead 2 iodide is that it's in a solid state, right? So what that means is that that will not dissociate, right? So because it's not going to dissociate, we simply rewrite this down here, PbI2 solid. All right? Now the potassium nitrate is in an aqueous solution, right? So therefore we know that this will dissociate to form 2K plus aqueous plus 2NO3 minus aqueous. All right? So that would be our ionic equation. So the next step is to determine the net ionic equation. All right? So how do we determine that? If you remember what we did when we looked at the net ionic equation for acids and bases, or for, I should say, the neutralization reaction, we look for the common items on both sides of the equation. Common items on both sides. So I want you to look at this equation here and tell me which items are common to both sides.
The potassium.
The potassium, that's correct. So we have the 2 potassiums here and the 2 potassiums here. Anything else?
The 2NO negative subscript 3s. Both
2
aqueous.
nitrates, right, 2
Nitrate.
nitrates here and here, exactly. And there's nothing else that can be canceled out. So the final equation, the net ionic equation is going to be 2I minus aqueous plus Pb 2 plus aqueous to give PbI2 solid. And that would be the net ionic equation for a precipitation reaction such as this. All right? Any questions about this one? Any questions? Any questions? Okay, so moving along, let's see what we have left to discuss in the last 15 minutes of this class. Oh, okay, so this is just a list of different precipitation reactions and their applications, right? So I won't go through all of this. I will just point out, for example, the first one where the precipitation of aluminum hydroxide is one that is applied to situations where you want to purify the water. Basically, the hydroxide would be added to the water if you have aluminum ions present. you end up with the gelatinous aluminum hydroxide being formed, which would be suspended and can be removed easily. And therefore you would have successfully removed all, if not most, of the aluminum ions present. You can also remove aluminum ions using this reaction here. Again, in this case, actually, this is used to remove phosphates by adding aluminum ions to it, and so on and so forth. I won't go through all the other examples, but you can read them on your own. But these are all applications of precipitation reactions. All right. Okay. Now, let's talk about redox reactions. We're going to start this and then complete this discussion next class. What do we mean by redox reactions? Redox is basically an abbreviation for oxidation and reduction reactions, all right? And basically, what happens in a redox reaction, let me just check the next slide here. There are several definitions for reduction and oxidation reactions, all right? You can have a definition based on what is called oxidation states, which we're going to talk about later on. So I'm going to leave that aside until later on, all right? I would say that a redox reaction is one where you have the transfer of electrons from one species to another. So let me just write that up here. A redox reaction is one involving the transfer of electrons from one atom to another. All right. So all the redox reactions that we're going to see in this section involves electrons removed from one particular atom of a compound or a substance to another atom of another compound or substance. All right. So how do we identify redox reactions? By looking at whether or not you have the transfer of electrons, or by looking at the oxidation numbers. So let me briefly talk about oxidation numbers. I'm sorry, let me go back to this here. Oxidation numbers, one way of defining them is basically it's a measure of how oxidized a substance is. And I know that's a bit redundant. I'm trying to find a page where, well, let me talk about oxidation first. So oxidation, we're going to deal with the numbers later on. Oxidation involves loss of electrons. We can look at it in that term, all right, for now. So oxidation involves loss of electrons, while reduction involves gain of electrons, all right? So there's a mnemonic that we use, or some people use, that they'll find helpful for remembering this, and that is oil rig, all right? And this stands for oxidation involves loss of electrons, reduction involves gain of electrons, all right? So hopefully this will help you to remember the difference between oxidation and reduction. Okay, so just to illustrate and give an example of a redox reaction, if you take a piece of, or I should say a coil of magnesium metal, and you dip it in a solution of copper 2 sulfate, all right? What you will see after a while, you leave it to sit for a time. What you'll see after a while is that the blue color of the copper 2 sulfate start clearing up. So it becomes more colorless. And you'll also see at the same time a deposit of metal being left on whatever is remaining of the magnesium that is in the solution, right? So what I'm going to describe here, or I'm going to write down here, is the actual equation for the reaction. So the reaction is magnesium, which is a solid, reacting with copper 2 sulfate, which is an aqueous solution, to form magnesium sulfate, which is aqueous, and copper, which is a solid, all right? So this is a reaction that is taking place. Now remember, the copper 2 sulfate is the blue solution, right? The magnesium sulfate is colorless, all right? As you sit and watch this reaction taking place, you'll see that there's a conversion from blue to colorless in terms of the solution itself, all right? Okay, so let's see what is actually happening in this reaction. If you were to, so this would be, again, the molecular equation. All right, so if you were to write down the ionic equation for this reaction, you'll notice, well, for one, the magnesium will remain the same, right? But the copper 2 sulfate is an ionic compound in an aqueous solution. So it will form ions, copper 2 plus aqueous, plus SO4 2 minus aqueous. And on the product side, you're going to have Mg 2 plus aqueous, plus SO4 2 minus aqueous. And then this copper here will remain intact, Cu solid, all right? So this would be the ionic equation. So to get the net ionic equation, just like we did before in the couple of examples that we looked at, net ionic equation, you look for the items that will be common to both sides and cancel them out, which in this case would be the sulfate ions, all right? So what you'll be left with is magnesium solid plus Cu2 plus aqueous to give Mg2 plus aqueous and Cu solid, all right? Okay, so this would be the net ionic equation. And if you look at this closely, you'll see that there's some changes taking place to the charges of the different species involved in the net ionic equation. You'll see, for example, that the magnesium here had a 0 charge on the left side, but over here has a +2 charge. So what that means is that the magnesium atom here is losing or lost 2 electrons, right? The magnesium atom here loses 2 electrons to form the magnesium 2 plus ion. Again, you're going to see some changes taking place with respect to the copper, right? You see here that the copper here is a +2 charge on the left, but a 0 charge on the right. So as you go from as you go from copper 2 plus to copper, what is happening is that the copper 2 plus is gaining 2 electrons to form the copper with the 0 charge, all right? So based on the definition that I mentioned before, magnesium is losing electrons, so therefore the magnesium is undergoing oxidation. And in the case of the copper 2 plus, it's gaining 2 electrons, so the copper 2 plus is undergoing reduction. All right? So this is a simple example of what we call a redox reaction, right? Where the magnesium is undergoing oxidation because it's losing 2 electrons to form the magnesium 2 plus ion, while the copper 2 plus is undergoing reduction by gaining 2 electrons to form the copper without any charge, all right? So this is what happens in every redox reaction. You have something losing electrons and you have another thing gaining electrons to form the products. And let me say this, and this will become important for future problem-solving exercises. In every single redox reaction, the number of electrons lost must be equal to the number of electrons gained, right? The number of electrons lost must be equal to the number of electrons gained. It is impossible for you to have a redox reaction where you don't have the number of electrons lost or gained being the same. They must be the same. And this will become important when we start learn how to balancing redox equations, all right? Okay, I don't think there's anything else I need to say about this, unless there are any questions about this. Are there any questions you have about this example of a redox reaction? Any questions? Okay, so I think I'm going to stop here. Okay, so I'm going to stop here for today. Before you guys leave, there are 2 things I want to say. One, you may have seen an announcement I've posted in Canvas. I won't be available for office hours today because I have a meeting which starts at 3. And based on past history with this particular committee I'm on, usually that meeting lasts for about 1.5 to 2 hours. So basically, I won't be able to sit for office hours between 3 and 5. You can contact me between 11 and 3, but after that, I have to attend that meeting, all right? So that's the first thing. The second thing is, and this is totally my fault, I didn't realize that according to the syllabus, you were due a test, the first test last week, right? So what that means basically is that I'm going to post by Monday your first test online, all right? In fact, there are 2 things I'll be posting. One would be quiz number 2 and test number 1, all right? Quiz number 2 will be based on what we covered in chapter 3 and maybe something in chapter 4. I've not decided yet. So I'll let you know about that. So both of those exercises will be due on Friday of next week. All right, so I'm just giving you a heads up as to what you should expect. As far as test number 1 is concerned, it will cover chapters 1 and 2. All right, I won't put 3 into it because I think chapter 3, I think I'll just put that in test number 2. So basically, test number 1 will be covering chapters 1 and 2. All right, and I'm going to, make an announcement about that. Just basically repeating what I just said just now. All right. So that's something for you to look out for. And I think that's it. That's all I have by way of announcements. So are there any questions you want to ask generally? Or, with respect to any topics or any concept or whatever? Any questions?
No, sir.
Yes, sir.
No, I do not have any.
Oh, okay. All right, so if there are no questions, that's basically it for today. So if you need to talk to me individually, I'll be available from 11 to 3, as I said before, but I won't be available from 3 to 5, all right? Okay, so that's it. Enjoy the rest of your day and your weekend. Take care. See you guys on Tuesday.